Welcome. So in this video we are going to look at L'Hopital's rule and limits where there is an indeterminate product. Now recall that L'Hopital's rule says that if I have the limit of a ratio of two functions that are differentiable and both are approaching 0 as x approaches a, or both are approaching infinity, then the limit of the ratio is equal to the limit of the ratio of their derivatives. Now we have to be careful. There's an extra condition that G has to satisfy, but in practice it's always met, and in particular in discourse it will always be met. So you don't have to worry about it. Now consider the following limit. So there's the limit as x approaches 0 plus, so 0 from the right hand side or from the positive side if you prefer. It is the limit of x times ln square of x. Now ln square of x is ln of x, which is squared. So there's a product of two factors, x and ln square of x. As x approaches 0, the first factor, x, approaches 0, of course. And ln square of x, well, it approaches infinity because ln of x approaches minus infinity as x approaches 0 plus, but because it is squared, then the entire factor approaches infinity. So we call that a limit of the form 0 times infinity. And that's an indeterminate form because we cannot just say that the limit is going to be 0 or infinity. In fact, it could be any real number. It could also not exist. So we cannot just tell what the limit is as of now, and we have to rewrite the expression differently in order to evaluate or determine more clearly what the limit is going to be. So one way of doing this is to send one of the two factors, x or ln square of x, in the denominator in order to rewrite the expression so that we obtain the limit of the form 0 over 0 or infinity over infinity, in which case we'll be able to apply L'Hopital's rule. Now you might say, well, there's no denominator in this expression. Well, you can think of x ln square of x as x ln square of x over 1. And then we'll be able to send one of the two factors in the denominator in order to rewrite that expression. Now, which factor do we send in the denominator? X or ln square of x? Well, that's hard to tell. Usually we copy strategies that have worked before, but this is our first example, so there's no way to tell. You just try one of the two and see if you end up with something that's easier. So I've started by sending ln of x squared in the denominator, and I get x over ln of x to the minus 2. Now ln of x to the minus 2, think of that as 1 over ln of x squared. So when x goes to 0 plus, that is of the form 1 over infinity, so the denominator goes to 0, and the numerator is simply x, so that goes to 0 as well. So we have a limit of the form 0 over 0. So I can apply L'Hopital's rule by taking the limit of the ratio of the derivatives. So the derivative of x is simply 1. That's why I have 1 in the numerator now. And the derivative of ln of x to the minus 2 is obtained by applying the chain rule. So we get minus 2 ln x to the minus 3 times 1 over x. Now the expression is not nice, and it's hard to tell what the limit of that is going to be. So what I typically do afterwards is I rewrite my expression to avoid having negative powers or complex fractions. So this simplifies to minus x ln cube of x over 2. So the x comes from the 1 over x that was previously in the denominator. So I send in that in the numerator, it becomes x, and ln of x to the minus 3 becomes ln cube of x. If you look at the numerator, ln cube of x will go to minus infinity. This still goes to 0, so we still have an indeterminate product here, and it's actually harder than what we had before because the power has increased by 1. That's typically not a good sign. So that means we're not on the right track. We have something that's more complicated than what we had initially. So that means we backtrack, and instead of sending ln square of x in the denominator, we're going to send x instead. So if we do this, in the denominator we get x to the minus 1, and that goes to infinity. So we get form infinity over infinity now. So we apply L'Hopital's rule again. differentiate the numerator, differentiate the denominator. I get, once again, a complex fraction and negative power. So I rearrange everything so that I can see if I've made progress. And if you look at the expression I have here, ln of x doesn't have any power anymore. So we had ln of x to the 2, now it's just ln of x. It's still multiplied by x, so we have an indeterminate product once again. So this is of the form 0 times minus infinity, but we've made progress. The power has gone down by 1. So the idea is to, once again, send a factor in the denominator to get a limit where we can apply L'Hopital's rule. So you keep on using the same strategy. Once something has worked, we've sent x before in the denominator, we're going to send x once again. So we keep on using the same type of factor in the denominator to simplify our limit. So by sending x to the minus 1 in the denominator once again, I get a limit of the form infinity over infinity. We apply L'Hopital's rule. We simplify so that we don't get negative powers or complex fractions. And now we get the limit of 2x as x goes to 0. And that's really simple because here we can use direct substitution rule. And we end up with a limit that's just 0. So this graph shows you the function f of x equals x ln square of x. And as you can see, as we're approaching 0, the function is getting closer and closer to 0, even though it's not defined at 0. So I can show you this by moving p along the curve, and as you can see, its y-coordinate is getting closer and closer to 0 as its x-coordinate is getting closer and closer to 0, which shows that the limit at 0 is 0 as well. Now our second example is the limit as x goes to infinity of x e to the minus x. The first factor goes to infinity, the second one goes to 0, so it's an indeterminate product of the form infinity times 0. The answer could be anything once again. We have to send either x or e to the minus x in the denominator in order to get a limit of the form 0 over 0 or infinity over infinity. Which one should we send? Well, we just have to try because we haven't seen any limits of this type so far. I've sent e to the x in the denominator, and the limit is now of the form infinity over infinity. By applying L'Hopital's rule, we get the limit of the ratio of the derivatives. The derivative of x is 1, the derivative of e to the x stays e to the x, so we get the limit of 1 over e to the x. And now it is of the form 1 over infinity. It's not indeterminate anymore because the answer is 0, because 1 over numbers are getting larger and larger and going towards infinity gives us numbers that are getting closer and closer to 0. If we look back at this limit, the limit of x over e to the x, we see that the answer is 0. So that means that going to infinity, e to the x is a lot larger than x. Even though x is getting large, e to the x is getting even larger. So that means that e to the x will dominate the polynomial function x as x goes to infinity. By applying L'Hopital's rule to the limit of any polynomial over an exponential function, we could show that that limit is going to be 0 all the time. So in fact, it's possible to show that e to the x dominates any polynomial as x goes to infinity. Thank you for watching.